All right, this video is going to be about indicators and buffers. There's not a ton to say about indicators. We'll go over what they are, do a little bit of work with them, but we're mostly going to focus on buffers. So indicators can do a bunch of different things, okay? So obviously you know about pH meters. We've already used them. We also have these different indicators that will turn different colors based on different pHs. So they'll be able to tell us when we hit a certain pH. So indicators are molecules that are one color or clear in molecular form and a different color in ionized form. Phenolphthalein is one of the most widely used indicators for titration. So this is usually how phenolphthalein is represented. It's H with phenolphthalein and then H plus and phenolphthalein minus. Okay, so this is its molecular form and then its ionized form. Phenolphthalein is colorless in acid and pink in base when it's ionized, okay? And I just told you that. Molecular, colorless, ionized, base. So if you wanted to talk about Le Chatelier, the base would change the direction of the acid. So phenolphthalein, very complex weak acid that changes structure dramatically. Adding base forces the weak acid to ionize into pink form. Molecular colorless, ionized pink. So different indicators will change color at different pHs. All right, so this is the generic indicator reaction. So we just did phenolphthalein, so we replaced IN with pH, but IN is just generic indicator. So the Ka of phenolphthalein is this, 1.1 times 10 to the negative 10. 10 times more or 10 times less of either the neutral or ionized form, it's considered the range of the color change. So you want to pick an indicator whose pKa is near the pH of the equivalence point of what you're doing. So you find out what the equivalence point is and then pick an indicator based on that. So for example, methyl red. If we have a Ka of 1 times 10 to the negative 5, we would expect this to be between 4 and 6. Okay, so if we wanted our equivalence point, or we expected our equivalence point to be between a pH of 4 and 6, we could pick methyl red. Before the equivalence point, it will be red. After the equivalence point, it will be yellow. All right, but that only works if we expect the equivalence point to be between a pH of 4 and 6. Okay, so that's what's really important about these indicators. So if you want to take a second, this should say methyl red. Which indicator would best determine the equivalence point of a titration of, I think that's sodium acetate, with a strong acid, HNO3. Okay, so we expect the equivalence point is about halfway through our curve. So right about here, 6.5 or so. So we would want to pick methyl red or bromothiamyl blue. Okay, it's going to be below 7. So, yeah, one of these two. Probably more methyl red, right? Because we're around 5. Yeah, we're probably going to pick methyl red. So we would go with methyl red for this one. And here we have the pKa's of the different indicators. So our pH curve, the best indicator for this titration would be, so we'll go to our equivalence point right about here. Around 8.5. So you want, like if your pKa is this, then you'll go from like kind of, so like for bromothymol blue, you would expect it to be from 6 to 8. For methyl red, you would do 4 to 6 and so on. So if we wanted 8.5, we would pick phenolphthalein, because that one's going to be from 8.3 to 10.3, and we're looking at 8.5. The pKa of phenolphthalein is likely to be around 9. We just looked at that on the last slide. But if you look at it from here, right, we would expect it to be from 8.3 to 10.3, so right about 9. So if you wanted to find it from this chart, there it is. Okay? So that's really like the gist of indicators. We'll do a couple more. So we just want to talk about choosing an indicator. For strong acid and strong base, there's a huge variety of what you could pick, okay? Because you can really pick anywhere on this curve and you're still going to hit the correct amount of milliliters, right? So if we picked this one, phenolphthalein, we would hit 50 milliliters. If we picked bromothymol blue, we would hit 50 milliliters. If we picked methyl red, we would pick 50 milliliters. So it's really easy to pick an indicator for a strong acid and strong base because our vertical is so long, okay? So the reason it's so much easier is because you have so much more flexibility there. For a strong acid or strong acid, weak base, or weak acid, strong base, or whatever, you want to be more careful about what you are picking. And the reason, we just said, the nearly vertical part is going to be smaller for the weak strong than it would be for the strong strong. So if you have a smaller, like let's say, for example, it was just like this little bit here, you need to pick the right one because you're not going to have as much margin for error there. Okay? And that's honestly pretty much it for indicators. You just need to be able to pick the correct one. Not a ton of stuff to do with that. But you're definitely going to want to make sure that you know how to do that. So let's start talking about buffers. So a buffer is, and you've probably heard this before, you've probably heard it in biology. If you've taken AP Bio, you've definitely talked about buffers. So a buffer is something that can resist a change in pH. So for not a buffer is water. You add a little bit of acid or base and it's going to change very quickly at pH. A buffer is something that can resist a change in pH, so it can it absorbs some of the acid or base that's added, okay? So for the pH to be stable, they must absorb it. So whether you're adding acid or base, there must be something in there to absorb it. So how does a buffer work? What's going to happen is that you're going to have a weak acid with its conjugate base, or a weak base with its conjugate acid. And you need to have significant amounts of both. Okay, so you know that when you put a weak acid in water, some of its conjugate base just pops out. Okay, or vice versa. You need to have more than that little bit. You need to make sure you have enough here, and these should be arrows. Okay, so there is going to, so that's that part. I just said that. There are going to be two ways that you can make a buffer. The obvious way is to take a weak base and add its conjugate acid as a salt, right, with like a pathetic attached to it. So you could combine HF, a weak acid, with NaF, because then you have the weak acid and its conjugate base, F minus, and the pathetic just kind of hangs out there. Or you can take your weak base, and add the conjugate acid with a pathetic. Okay, so that's an easy way to make the buffer, the obvious way. The secret way, and we talked a little bit about this in the titration video, the secret way is to partially neutralize an acid or a weak base with the opposite strong. Because you know that when you neutralize, you are creating the conjugate, right? We talked a lot about that in the titration video. When you have a weak acid and you neutralize it with a strong base, you are creating the conjugate base. So if you only partially titrate it so that it's not at the equivalence point, you're going to have that weak acid with its significant amount of its conjugate base. Okay, so this goes directly back to our last video. So you need to be careful about that because you'll be asked a lot about buffers, and you want to make sure you know that there are two ways, and don't forget about that second secret way. Okay, so let's start talking about some questions. What is the pH of a solution made with equal moles of acetic acid and acetate ion? Okay, so obviously this is attached to a pathetic of Na, but it's acetate ion, its conjugate base. So when weak acid equals weak base, because we said equal moles, your pH is going to equal your pKa. Okay, that's like our half equivalence or whatever. So your pH equals your pKa. Your pKa, if your Ka is 1.8 times 10 to the negative 5, your pKa is going to be 4.74, or close enough to this. If you don't have a calculator, right, I wrote no calculator, so you can try it without a calculator, you would know it would be 4 point something because of this negative 5, right? Those are the log rules that we talked about. So we would know it would be 4 point something. That's our only option here. All right, a mixture of 0.1 moles of NH4Cl and 0.1 moles of NH3 is added to enough water to make 1 liter of solution. Which particles make the solution a buffer? We know that a buffer needs to have its weak acid or weak base and its conjugate. Here we have a weak base, NH3. We need that. And we also need its conjugate, NH4 plus. Cl minus doesn't matter. It's a pathetic. It's there. Great. We don't care. A mixture of 0.1 moles of NH4Cl and 1.1 moles of NH3 is added to enough water to make 1. Which equilibrium expression could we use to calculate the pH of the buffer? It does not matter. For this one, you would use Kb and the OH minus, and then you would 14 it. For this one, you would use Ka and the H3 plus or the H plus, and you would just negative log it. So either one of those is fine. You're going to get the same pH because it's the same solution. All right. If some HCl were added to this is the same buffer, which substance responds to neutralize the incoming strong acid? If we have a strong acid coming in, we need a base to neutralize it. Cl minus, even though it's minus, is a pathetic, so we don't care. And an acid cannot neutralize an acid. The equation would be HCl, which we'll just write H plus, because HCl is a strong acid, so it dissociates immediately, plus NH3, gives us NH4 plus. And yes, NH4 is a weak acid, but it's going to take away some of that H+, so it is going to neutralize it. Okay, so this is what a lot of questions will be like for buffers, and you're going to have a practice tomorrow in class that's, is this a buffer or not? And you have to go through and make it up. Okay, so which of the following combinations will result in a buffer? Will the pH be 7, above 7, or below 7? So this one is a strong acid and pathetics, no buffer. This one is acetic acid, and it's a conjugate, so it's going to be a buffer. And the pH will be below 7. So this one is, and the pH is below 7. Number 3, we have a weak base and it's conjugate acid, so that is a buffer. And the pH will be above 7. The reason that the pHs have to do with the Ka, okay? So if the Ka of acetic acid is -5, that means the Kb of acetate is what, probably -9, right? Because Ka times Kb is Kw. So that means acetic acid is better at being an acid than acetate is at being a base. That's why we have -7. Here we have NH3, Kb is -5. So that means Ka for NH4 plus, it's going to be -9. So NH3 is better at being a base than NH4 is at being an acid. So we have pH greater than 7. Number 4, we have a strong acid and pathetics. No buffer. As soon as you see a strong, you know it's not a buffer because it has to be a weak. So with that said, go on to another. This is a weak acid. I shouldn't have said as soon as you see a strong, it's not a buffer, because you could be using the secret way. So I take that back. You could be using the secret way, but if you see a strong with its pathetic, then it's not a buffer. Okay, so if you see a strong and you see it's pathetic, or you see other pathetics, it's not a buffer. But if you see a strong with a weak, it could be a buffer. It could be the secret way of a buffer. So here we have a weak acid and a strong base. So we could have a buffer, but look what we have. We have 25 mils of the acid, and they're the same molarity, right? So 25 mils of the acid, 50 mils of the strong base. We are way past the equivalence point, which you remember from titration means that we're not even talking about the weaks anymore. We're just talking about the strongs. So this is super not a buffer. It's going to be very much past its equivalence point. So here we have strong acid, strong base. Strong and strong are never going to be a buffer. Here we have weak base, strong acid. So we could have a buffer. We need to look at the amounts. We have equal amounts, 100 mils, 0.5 molar for both of them. That means it's at the equivalence point, not a buffer. Okay, we have no more. If we're at the equivalence point, we have no more of the weak base left. So number 4, we have a weak acid weak base with a strong acid. But yes, we are not at the equivalence point here. Okay, we have 100 mils of the weak base. We have 60 mils of the strong acid. So that means we have not neutralized the entire weak base yet. Okay, we would have to have more of the acid. So that means we've partially neutralized the weak base, which is the secret way of making a buffer. It is the weak base partially titrated, which we now know means from our last video, we have created some of that conjugate acid. So this is a buffer, and the pH is going to be greater than 7 because we haven't hit that equivalence point yet. Right? So if you think back to our titration problems from last class, before we hit the equivalence point, we're still in that basic area. And again, we are going to have just practice on this tomorrow, where you're just saying, is this a buffer or not, and going through this. So we will have plenty of practice with it. So make sure you take good notes on those, and if you need to go back and review them again, do that, but you are going to have a whole practice worksheet on it. All right, so let's go to some other types. Calculate the pH of a 0.025 molar nitrous acid solution. Okay, so these are just some other types of questions. So here we're going to do, this is an x squared problem. Ka is going to equal oops, I don't know why I put x equals. So that means x, which is H plus, is going to be this. And then pH is this. All right, so this one, pH is solution. We have sodium nitrite and nitrous acid. Okay, so here we have a buffer. We have our weak acid with its conjugate base attached to a pathetic. So we are going to have a buffer. Buffers don't always have to be pH 7. That's a very common misconception. Buffers can be at any pH. You can make a buffer at any pH. So here, we don't necessarily want to say, okay, it's 7 because it's a buffer. You need to do the work, okay? So we're going to use our Ka expression. And we know that for all of our Kas, they look something like this. So we'll just use our generic one. And we know we're going to have 0.05 of HNO2, which is our weak acid, okay? We are going to have 0.03 of the nitrate. Nitrate is its conjugate base, so that's A minus here. And then H plus we're going to find by setting it equal to our Ka. And your pH is this. So this is a buffer, but its pH is going to be 3.12. All that means is that the buffer is going to stay at that pH, even if we add little bits of either acid or base. And if it's helpful for you, if you don't like the generic one, you can always write the Ka, just like we did in the problem before. Okay, that's the same Ka we had before. So you can use the generic one, or you can write it out for your reaction. Either way is fine. All right, so now we're back to a buffer question. Which of the following combinations could produce buffer? Not this one. You have a strong acid and it's pathetic. Okay, so we know that's not going to work. So this one's a little bit, these lists are a little bit different than the other one because we don't have amounts. What they're saying is, could it produce a buffer? Like if we had the right amount here, could it produce a buffer? It's actually it's a lot easier because you don't have to do any math for it and figure out, is it past the equivalence point or not? You don't have to worry about that. So here now we have weak acid, weak base, but they're not conjugates of each other. We don't have anything that's a conjugate of the other one, so no. You must have a conjugate. Most likely AP wouldn't ask a question like that, but it's important just to know, just in case. So here we have a weak acid with its conjugate attached to a pathetic, so yes, that is a buffer. Here we have strong acid, strong base. We know that's not a buffer. Here we have weak acid, strong base. Okay. Here we would say yes, it can be a buffer if before equivalence point. If it's only partially titrated. Okay, we don't know the numbers here. It's a little easier than our last one. So we'll just say, yeah, we can have one. And then here we have a weak base with its conjugate. So of course we could have a buffer there. That's the easy way. So when you're doing these types of questions, make sure you're paying attention to the secret way, which is this one right here. When you have a weak with a strong, they can make a buffer. It just depends on the amounts. Okay, so we are going to find, we have HF, H plus F minus. Okay, so this is a Ka kind of problem, but we have some F minus already. So we have a buffer here. Okay, so we have our Ka, H plus, F minus over HF. H plus we don't know, but Ka we do, 6.8 times 10 to the negative 4. H plus, our F minus is going to be 2.2, excuse me. And then we have 0.05. So when you do that math out, you get H plus is equal to 1.7 times 10 to the negative 4. And of course, you don't need to know volumes because you're given molarity. Okay, so that last one doesn't make any sense. So here we're looking for the pH. We have 0.5 molar sodium acetate, 0.5 molar acetic acid. So we know that they are equal to each other. Okay, when the weak acid concentration equals the weak base concentration, the pKa equals the pH. Well, I guess not weak base, so we'll say conjugate base, right? So 4.74. pH above 7, equal volumes. So for equal volumes, you know the pH is going to be equal to the pKa. Okay, so if we went with equal volumes, okay, so this isn't a buffer at all, right? Because it's a strong acid and it's pathetic. This could be a buffer. This can't be a buffer because it's strong and strong. This could be a buffer because it's weak acid and it's conjugate. This could not be a buffer because it's a weak base and a weak acid, but they're not conjugates of each other. So it has to be one of these two. All right, so you would look at this one or this one. We know that when they're equal volumes, pKa is equal to pH, so the best one to get a buffer above 7 is going to be this one, because its pKa is above 7. All right, so this is a lot like the one we just did before, but since these are not going to be equal molarities, we did 2 slides ago, but these are not equal molarities, we can't say that the pKa is equal to the pH and just pick 4.74 this time, because this time we have 0.5 and 0.05. So instead, we need to set this to the Ka. Okay, so we have the pKa. Yeah, so we have the pKa. So the Ka is going to be equal to 10 to the negative pKa, 10 to the negative 4.74. So that comes out to be 1.8 times 10 to the negative 5. We're going to set that. So Ka, our Ka expression is going to be H plus times, the conjugate acid, so it will be acetate. I'm just going to put A minus over our weak acid. So we have 1.8 times 10 to the negative 5. And our acetate is 0.5. Our weak acid is 0.05. So our H plus comes out to that. And when you do the negative log of that, you get 5.74. So here, if we had a buffer, our weak base, conjugate acid, our reaction would be this. You could also write it from the weak acid perspective, it doesn't matter. What will happen if a small OH minus is added? So Le Chatelier tells us if we add more of this, it's going to shift this way. So NH4 will decrease. So not this one, not this one, not this one. Not no change, not no change. Okay, so NH4 will decrease, NH3 will increase. Is the pH going to increase? Yes, we're adding OH minus. If we're adding OH minus, the pH increases. pH of a buffer solution, 0.2 acetate, 0.3 acetic acid. Okay, so this is the same as the one we did a couple slides ago, except instead of 0.5 and 0.05, we have 0.2 and 0.3. So our Ka, you can find it again. It's going to be the 10 to the negative pKa, but we already know from a couple slides ago that that is this. And we're going to do H plus. And then our acetate is 0.2. And if you want to see the pK and everything, you can go a couple slides above. But we already did that, so I don't think we need to again. H plus this time comes out to this, which means pH is this one. Okay, so which of the following conjugate acid-base pairs is going to not function as a buffer? It's this one. Okay? You can't have a strong acid and it's pathetic. All the rest of them don't make any sense. You can say that this isn't a base because it's a conjugate of a multiprotic acid. And spectator ion is just another way of saying pathetic, and we know that that's not one. Okay, consider a buffer solution containing 0.3 moles of acetate and 0.3 moles of acetic acid, to which 0.1 moles of HCl are added. The pH of the solution will decrease. We're adding acid. Okay? Even if it only goes down a little bit amount because it's a buffer, it still goes down. It's going to go down a tiny, tiny bit, but your answer is going to be decrease because the opposite is stay exactly the same. If it said something like stay about the same because it's a buffer, okay. So this would still be a buffer even when you add a little bit of HCl, okay? There is still about 3 moles of acetic acid and 0.2 moles of acetate, so you're going to be fine. Well, 0.3 moles, not 3 moles, 0.3 moles. So when the amount of one conjugate is about 10 times greater than its pair, so if we had like the acetate be 10 times greater than the HCl or the other way around, then it's not a buffer anymore. It exceeds what we consider the buffer capacity. So the buffer capacity is going to be 10 times whatever one is staying the same. So it would have to be a lot more than 0.1. And that's it for buffer.